muchas gracias. ¿Se me escucha bien? Sí, creo que sí. Soy Oriol Lehmkuhl, soy investigador Ramón y Cajal en... ¿Qué? Sorry. Yeah. I'm Ramón y Cajal researcher at BSC. I also have an ERC and focus it on fluid mechanics, integration with machine learning, HPC, and experimental works for high-speed flows. I particularly work in aeronautic fields, no? And when I was invited to this panel, it was a pleasure to accept. I own a lot to the rest. As Sergio was saying, 20 years ago, I was at UPC. We were building our own small clusters using desktops, putting internet network between the desktops and trying to do something relevant there. It was very hard because maybe each desktop has one core or two cores at that moment. So at the moment that Mare Nostrum was available, it changed our life. And we were, at one moment, really able to compete with Europe, to compete with United States. And right now, in my group, we are simulating full aircrafts for Airbus and doing better simulation work than maybe our colleagues in Germany and France. And this is thanks to RES. So I owe my career to this network. And here we have some of the users of RES that use more and more hours. And most likely, we will not be in Spain without this infrastructure. We will move to other countries. So it's a pleasure to me to help on this panel. We will focus on how we are using deep learning and IA in engineering. I believe that our conclusions can be extrapolated to other science domains, okay? Because most likely we are at that moment that we are experimenting, trying to understand how to use these tools. And I hope it's a nice panel. No? We have Eusebio Valero from Politécnica of Madrid, Sergio Hoyas, Bernat, and Elena Martín, that I will pass now the floor to you guys in order that you do a short introduction about your background for the audience to understand a little bit, which is our book, no? That, of course, our opinions are linked to that. So, Eusebio, first.
Okay, thank you, Oriol. So my name is, already Oriol mentioned, is Eusebio Valero. I am full professor of applied mathematics at the School of Aeronautics. In fact, my background is aeronautics. I studied aeronautics a long time ago in my school. In fact, I was just teaching a long time ago Elena Martín. That is sitting here. And then my PhD was also about aeronautics, fluid mechanics. And then I started working in computing after my postdoctoral stay at Von Karman Institute. No? And since then, that was 20 years ago, more or less, we started working in computation. Normally, computation applied to fluid mechanics works. And we have seen somehow the evolution of the computation in close relation with the industry. No? We have been developing numerical methods in my group. So we have, I am leading a group of around 20 researchers. No? That is a combination between fluid mechanics and numerical mathematics and also applied mathematics, of course. So I think it's a very good combination with a lot of possibility in the aeronautical industry so far. No? And during the last year, we have somehow see how the computation is evolving in our aeronautical world. No? We have started working also with the group of Barcelona a long time ago, and also with the group of some members of my team also working with Sergio and with Bernat a long time ago. No? We haven't still the opportunity to work with Elena, but for sure that we'll have the opportunity to start working with them. And at the beginning, everything was about numerics, and however, in the last 3 or 4 years, we discovered artificial intelligence. And now, I think that it's not possible to think in simulation without artificial intelligence. I think that is opening a new field, completely new field. With this, the role of artificial intelligence, combined also with numerical methods, no? Like opening new possibilities to create new numerical tools, able just to do everything, design, optimization, prediction, much faster. No? So this is somehow the idea of our group. So in this sense, most of the projects that we are normally managing or the projects we were involved are related with artificial intelligence. In particular, we are now also with Oriol, a IRC Synergy grant, no? That was granted this year with 10 million euros, just funded by the European Commission and also in collaboration with Purdue University. And one of the core of this project is basically develop a model for artificial intelligence used for fluid mechanics purpose. So this is somehow a little bit the idea. Okay?
Sergio?
Okay. Good morning, everybody. My name is Sergio Hoyas, and I am professor of aerospace engineering at the Universidad Politécnica de Valencia. And my field of work is turbulent flows. It's great to be here in the 19 because I was at the very beginning. In fact, I think that maybe I was the first user of Mare Nostrum or something like that. Probably was the first external user. And we were working from the very beginning doing a very large simulation that, by the way, has 1,400 citations right now. So yes, it was a very large simulation, and we were really successful. And the point is that after 20 years, we are still doing basically the same, only that in larger supercomputers and taking more and more processor and more RAM memory. And in fact, we are preparing one simulation with Oriol that every snapshot will be around 24 terabytes of data. Okay, just one instant of the flow, 24 terabytes. So the point of artificial intelligence here is, okay, so you got one database of, I don't know, 1 petabyte. And how do you extract useful information for designing one plane 20 years from now? How do you do that? Extracting information from one petabyte database. And moreover, can we do something different? Because right now, if you are, I suppose that you know that the Navier-Stokes equations, the equation of fluid mechanics, cannot be solved. Okay, analytically, it's impossible. And the point is that we still are restricted, so let's say it's very simplified flows. Okay? So for many, many years, people had a very good idea, and then we start working on that idea, but there is not a very basic, fundamental approach. Somebody has a very nice idea, and we start going in that direction. But there are still a lot of discussion, even for very small details. So some years ago, with another colleague, Ricardo Vinuesa from KTH, and now in the University of Michigan, we started thinking, okay, can AI help us somehow? So the first thing that we did was to develop one network in order to advance from one step to another one without using the Navier-Stokes equation, simply with this convolutional network. Once we had that, we said, okay, imagine you take a look to a river, okay, and you see a lot of eddies, a lot of wheels moving around. There are many possible definitions of these eddies. We compute all of them in one flow, and with one algorithm of explainable artificial intelligence named SHAP, we ranked all of them. And we saw, okay, these are the most important for testing. And we have an explanation, because the point is that with explainable artificial intelligence, we were able to rank everything. This was published in Natural Communication, and this week, we had very good news, because we have advanced that, and now we have done that pixel by pixel, defining some new eddies, new wheels, just simply using artificial intelligence. It's an artificial intelligence definition of an eddy. Okay? What is the next step? Apart from the simulation that we are doing with Oriol, we have run another simulation, just a very small piece of a wing. This very small piece of a wing gave us one database of around 200 terabytes. We are analyzing that, and for the first time, we think that in some months, we will be able to unveil the mechanism causing friction, and what are the most important mechanisms related to friction. And with that, we will be able to try to control friction and reduce the waste of fuel in aviation, for example.
Okay. Bernat?
Hi. Thank you. I am Bernat. First of all, I want to thank the invitation to be here. I think this is a very nice opportunity for us to discuss how we are advancing in AI, and probably in our particular case, mostly fluid mechanics, but we can try to generalize. So I also come from the aeronautical school of the Universitat Politécnica de Catalunya. This is where I did my undergrad studies, and then I moved to the UK for my PhD in CFD and turbulence modeling using AI. And I also spent some time in Singapore during my PhD. And then is when I went back to Barcelona Supercomputing Center for my postdoctoral study. I worked there with Oriol. And actually, it's one of the places I started using AI in a more large-scale manner. We defined some big cases that we wanted to control turbulence or doing active flow control with reinforcement learning. And we achieved some very good results there. And it's not only coming from our own, let's say, research ideas that made that happen, also the infrastructure around us. So we make a great use of Mare Nostrum 5, which is an amazing machine. It's very well supported. I've been using supercomputing clusters around the world for many years now. And I'm very happy to say that the Mare Nostrum 5 is amazing in that sense. So that enabled us to make these great discoveries. And nowadays, I'm focusing on this specific field, on fluid mechanics with AI for active flow control, for turbulence modeling, and for accelerating the simulations of the Navier-Stokes equations. As Sergio was saying, these are very expensive. So this is how AI probably can help us to make them faster and cheaper. Thanks.
OK, and Elena?
So thank you very much for the invitation. It's a pleasure to be here. And also, I want to extend also thanks to the Spanish Supercomputing Network, because it allows, as it was said before, it allows even small or medium research groups to have access to that computing system. And it makes really a big, big difference for small groups like ours. So thank you very much for that. It's a great, great work you are doing. Well, I'm full professor of fluid mechanics too. I come from the Polytechnic University of Madrid, but I've done most of my research at the University of Vigo in Galicia. And our small research group do basically solve a lot of different problems that involve fluid mechanics, but we are like multidisciplinaries, in trying to solve multidisciplinary problems basically for the industry that surrounds us. Although we are doing lately some work for the European Space Agency and detonation engines and more aeronautic problems, solving more aeronautic problems. We started like 15 years ago, trying to solve more industrial problems, like solving what is happening in a big furnace that are 32 meters long. They spend megawatts of power just maintaining the heat in that big digital furnaces. So they had a lot of problems controlling the temperature inside of the furnace. They wanted to save money, and they asked us, can you do a predictive model of what is happening here in this furnace? And we said, OK, this is different to any fluid mechanics problem we have dealt with. But we started at the beginning with a more common approach, that is to do computational fluid dynamics. And then we realized that we needed to go to a more fast tool, to give to the industry something they can use and they can put inside their control algorithms. And that's the way we started to work with machine learning, and then more lately, more artificial intelligence algorithms right now. So it started with thermal problems in, as I told you, metallurgical industries, wood industries, automotive industry, and then also we apply it to the aerospace engineering industry. So this is what we basically do.
OK, thanks. So the idea is to follow 5 questions. On each question, you guys, if you want to really answer first, you just tell me, right? And if there is in the audience someone that wants to give his opinion or her opinion, or something is not clear and you want more details, just put your hands up and And we would like to do it as interactive as possible, okay? So the first question has been a little bit already tackled, okay? But just for each of you, the idea is that you explain what is more exciting for you about the IA, no? So maybe it's flow control, maybe it's integration of IA inside your numerical schemes. This is the most exciting for me. I believe there is a lot of potential right now. So at this moment, maybe people is focusing too much on just using IA, but this fusion between what we know, traditional numerics, traditional fluid mechanics, and IA is where the big gains are. And we are realizing this as a community. Or maybe you are more excited about the interaction with industry, no? Maybe it can speed up this interaction with industry. So I would like to have your point of view and see what discussion we can have about this. So,
okay. Maybe you can start again.
Yeah.
What is my opinion about IA? Normally, when we had to, for instance, at the School of Aeronautics, we work with industry a lot of this is one of our somehow success, no? Because we have been working for a long time with, in particular, with Repsol. We have developed numerical simulation tools with Repsol, Airbus. We are participating also in developing the numerical solver of Airbus, and also with ITP, propulsion industry, with Rolls. So we have a lot of background about what are the needs of the industry. In general, the numerical simulation, the role of the numerical simulation from my point of view is to generate a model. No? They want to understand in advance what will be the behavior of some particular configuration. That can be a complete aircraft, it can be the structural, it can be the dynamic, it can be the acoustic, it can be the combustion, the propulsion, or it can be just the aerodynamic. And normally because aeronautical industry, there are very complex configurations, means that to solve only one configuration, some time ago, even now, can take days or even months, no? Just depending on the accuracy and the details of your simulations. No? For a normal design of aircraft, you need around 100,000 simulations. This is typical order of magnitude if you want to design something new. No? It is not completely new. You want just to optimize, so maybe the number of simulations will be lower. No? But in any case, you have to do a huge number of simulations. To do this number of simulations, no? Just before going to the wind tunnel testing, because the wind tunnel testing is very, very expensive. You have to create a model, you have to manufacture a model, and you go to the wind tunnel. The wind tunnel really is very, very expensive to manage. So then there is a preliminary work using just simulations. But simulation is the integration of the Navier-Stokes equations, like Sergio was mentioning. No? But the integration of the Navier-Stokes equation using numerical method is also very expensive. No? For complex configuration, maybe simple configuration, no, but in complex configuration is very expensive. No? So now with artificial intelligence, it's possible to create a new model. No? This opens new avenues of a new field, a completely new field, to create models that are very, very, very cheap and very, very, very fast. No? So that means that maybe you can create a model in order to run. So you need to run 100,000 simulations, so maybe you have to run only 10,000 simulations, and then you have to create the model with these 10,000 simulations, and then to run the remaining of these 90,000 simulations with the model. So that means that your design process will be very, very quick. No? The main problems are obviously the accuracy of your model. No? So normally we trust that the accuracy of the numerical models is good enough, and we still don't know if the accuracy of the artificial intelligence model are good enough. No? That is something that is still open to the scientific community. But from my point of view, this is the new field of application. So somehow there is some maturity about models of language. No? But the application of these methodologies, of these kind of algorithms, to the aeronautical industry, in my opinion, is still in the beginnings. No? And not only aeronautical industry, I think that also in structural and all the kind of fields, no? We are still just putting the stones of all these stairs, no? Little by little, just to create all this kind of new field of application to this machine learning methodology. Okay?
Yeah, I think that, it's what you said about the numerical simulation, about to try to accelerate everything and to create models and to create, for example, I think that maybe in the future we will see a lot of prompts reduce of their models, because this is one of the other things that we have to do. But I would like to split this field into two parts: the most scientific part and the most applied part. science and engineering. From the point of view of engineering, well, I'm not in that field, okay? I'm more that in the science part. And from the science point of view, I think that the most incredible part of artificial intelligence is that for the first time in many, many years, we have a new tool. And it's something new, because as I said in my first intervention, what happens is that you have an idea. Then you try to use that idea in order to understand something. But at some point, you reach a wall, and you don't know how to continue. The good point about artificial intelligence is that we are climbing that wall. We are passing that wall, and we have something new to work with. So it's about understanding and maybe also using DRL, deep reinforcement learning, together with all the information that we can extract from the flow to obtain something new, a new tool to control the flow, and to give to the most applied people one new tool in order to improve all these designs. Maybe you can put that later in a plane or not, because this is also quite difficult, okay? But at least we can advance. Because until now, until, let's say, 5 years ago, most of the ideas in fluid mechanics was just very incremental. We are working in this little epsilon more, and we are advancing this bit more. And now we have an explosion of papers, because we have a new tool, and people are using this tool very much. For example,
I love this idea. I love this concept. It's true. So traditional, I would say, continuous mechanics, no, applied to engineering. The early years was in 50s, 70s. They did everything, and what we have been doing these last years is to do perfection of that, no? Do we go more efficient, use better resources, better computers, etc., right? But there is no new algorithms in the sense that it's disruptive, no? It changed the way that you can understand the questions, that you can solve the questions. And right now we have this explosion. It's true that on the explosion there is usually too many ideas. I think people has a lot of hurry to publish fast, no? To have something that maybe is very particular yet, is not general, we are not up of the standards that we were having on the traditional methods. But it's opening doors to understand the questions and the physics from other points of view. And here, I believe, we have a lot of opportunities. Yeah.
Yeah, let's say an older scientist than me that works in a school, very like Eusebio in the same school, told me that we are probably not smarter than them, but we have better tools.
Yeah,
so
that was the typical, you know.
I took it in the right way.
Yeah. Bernat.
Yeah, this is a very good point, and I think we can learn a lot also from other fields. So, of course, in fluid mechanics, I think we jumped into the AI wagon maybe, I don't know, maybe about 10 years ago or so. Then we started to develop all these, or exploit all these new tools. We are learning how to use it, how to interpret them, which is another key point. Like, do we want black box models, or do we want to try to understand the physics behind it? This is probably related to the SHAP work that Sergio is doing. But there's a lot of successful stories, I think, that has been happening outside of fluid mechanics. For example, we use it for active flow control, reinforcement learning, but only last year, I think, there was this new algorithm to just do matrix-matrix multiplications discovered with reinforcement learning that was faster than any other algorithm that has been tested to that point. And this is critical. Like, we do matrix-matrix multiplications in every algorithm almost that we have. So this was like a very significant discovery from AI only that can, improve a lot of systems. We also use it for drug discovery. We also use it for materials discovery. You have a very high dimensional space of different components or compounds for drug discovery. You want to try to, for example, predict toxicity or predict efficiency of a new drug, but you cannot just create all of them. You want to target something, then you reduce it. You reduce this dimensional space to something which is ranked by whatever machine learning model, and you test only those compounds that are predictively better. Or for example, in weather forecasting, it's also quite amazing what it has been achieved lately. So you have weather models now that are made with machine learning that compete with traditional standard weather models, and they are much, much cheaper to run. So because we rely on an ensemble of models, if you can have an ensemble of AI models to predict weather forecast, then you can for surely get at least as good predictions, but much faster. So there's a lot to learn from all these fields, I think, and this is what really excites me about in fluid mechanics, like learning from that and applying it to turbulence, to flow control.
And Elena?
I'm going to talk more about the practical sides of the use of artificial intelligence, because I consider myself not as a developer, but as a user of the algorithms and techniques that come up all the time. For me, what is exciting about artificial intelligence is what I said before. We have a very difficult problem that it's very expensive to run, and how the artificial intelligence can turn that expensive, high-fidelity models into real-time tools, so that the industry can do with these real-time tools whatever they want, or control a process, or do an optimization of a multi-parameter space that was not it was impossible before, because some industrial processes depend on a lot of different parameters. And what I saw in the industries is that basically they run the processes with a given parameter, but they don't know if they are optimized. So they just don't know, okay, can we save money, but still having a good quality in our product? So the questions they are asking themselves, basic questions, no? They spend a lot of money in energy in that industries. What I see is a revolution that, and what we are trying to do is bringing all that small, medium, and large companies to use artificial intelligence. And for them to start, even basically if they are small and medium companies, it's very difficult. They don't have experts in CFD, they don't have experts in artificial intelligence, they don't know how to use those resources, or even how to ask for those resources. So I think what would be grateful, and I see a lot of actions in this direction from the rest, it's bringing that gap for the small industry and medium industry, so they can use and they can have those models, they can have that expertise, they can have access to that computation. So that's
very interesting. We will tackle a little bit this on some of the questions. I don't know if we have any comment. No? So the next question I wanted to talk is about that we are merging traditional HPC with machine learning, right? And we have a lot of challenges. I would like to know your opinion. For instance, traditional HPC, have specific languages that we are moving to GPUs. Could be CUDA, OpenACC, OpenCL. I don't care. There are so many variants. But machine learning is using layers of Python, usually very focused for one GPU. There is not that much well optimized for multi-GPUs, depending, some things yes, but depending which architectures and things you want to do, there is a lot of challenge. Then we have the scientists that they need to learn one part, the other part, and they need to merge. I know Bernat, his answer. We can begin with Bernat, because okay. I believe he is excited to talk about Julia. He liked it.
Okay.
But there is a challenge here as well, if we really want to push this at the scale that we were talking, how we are merging all these different tools in order to really do large-scale scientific machine learning, no?
Yeah. So indeed, right. So we've been coding like HPC solvers for physics in general with Fortran, with C++, and now we're trying to do a flow control, which is a PyTorch model, right? And then how do you make them talk one to another? There are many ways to do it, and it's okay to have this two-language setup that you want to send data to the solver to the model and the model to the solver back and forth. But it's not very efficient, and there are new languages that have been emerging lately. And one I am very happy to use and to talk about it is Julia. This is why Oriol was making the joke, because I'm a bit of a fanboy of Julia, maybe, if you want. But it's true that it was designed for this idea. It was designed for scientific computing. So bearing in mind that scientists that do heavy computational workloads need to have their low-level access to the code. We still need to write like for loops and be able to compile them and run them faster, but integrate them with a high-level library. For example, if you think about fast Fourier transforms, right? This library has been available with the FFTW for C++ and for Fortran since forever, and we take it kind of for granted that we can use it in Fortran and C++, right? But we don't have the same kind of analogous library for machine learning. We don't have something that we can just compile, plug in, and play with. And this is kind of a bit of the promise of Julia, that you can write code like Fortran and then use high-level libraries like PyTorch in the same setup. And you also benefit from parallelism at different layers, at the shared memory or distributed memory layers. And you have also, you can also design code for GPUs, for any GPU architecture, which is also one of the problems that Oriol mentioned. We have to learn now to make GPU code for different architectures, not only GPU code in general sometimes. And this makes it a bit tricky. So this is one of the things that I'm excited for scientific computing.
Yeah. I think that we have a very big change because, for example, when you said Fortran and FFTW, when I was doing my code, I knew the memory that I needed at every step. And I knew, for example, that the FFTW that I compiled, or I used that library everywhere, at every moment without any problem. Just the only thing I needed was the module that I have to use, or the flag. That's it. And I knew the memory of my code at every moment, at every step. But now I'm using this library on Google, TensorFlow. Mm-hmm. And the problem is that I know that at some point I got a problem with the memory. I started digging up and digging up and digging up, trying to see where I'm using that memory, how to improve that. Impossible. Impossible. And apart from that, I need the version 13.7.2 that comes from Python 12.4 that needs Linux 6.32. So I think
it's a great point. We have a problem of standardization, I believe, on the machine learning libraries. And this is a barrier to really reach all these big supercomputers across the world, right? We are used old school, guys that we have been using supercomputers for more than 20 years. Always, we have been doing our own code, controlling everything, being sure that it's portable across a lot of things, because we are trying to use all the machine, the maximum memory, the maximum efficiency. But right now, with these libraries, we have not this control. And in the other side, each of the students is using a particular flower that has a particular different dependencies. And we are all the time asking support, put these new modules, etc. It's a pain, and it's a big barrier that we should be able to solve if we want to be serious on that. Yeah. I don't know, Eusebio.
I have to recognize that my level of language programming is not your level.
I know.
And I have been programming for maybe 15, 20 years in my life. No? I did my PhD in C. And then our in-house solver and programming in Fortran. No? So I have experience. I also have experience in Fortran and C. No? And I stopped in MPI. So we realized at the beginning, at the university, we were programming in fact, also in industry, because we were in close collaboration with industry. I have seen the evolution of the language programming during these years. No? I think that the university is more advanced than the industry at this level. No? So we started with serial code, C, C++, Fortran, and then we moved to parallel code with MPI. No? And then we started just with Fortran, the standard of Fortran 90, Fortran 20, 2000. So then you start just with parallelization inside the programming languages. And then suddenly GPU appears. No? And now everything should be in GPUs. What is the problem? So sometimes you're going to get rid of your solver and then to start from scratch. No? And this is difficult. So normally we try to adapt our numerical solvers to the new GPU mentality. And we realize about that. We realize that with Python, the standard of Python should be 3. For Python is not standard with 4.6, and then you have just to manage, because every time that a new standard of Python, so that means that you have to change a lot of lines and nothing works again. No? And now appears the world of machine learning, which is everything is related with Python. So there is a feedback with the machine learning in your solvers. No? And we have to adapt. This is evolving very, very fast, no? At least to me, not for my students. No? So normally my student complains about all these kind of things that you complain, and I say, you have a problem, but you have to solve it. I don't know how. No? This is the discussion we have almost every week. No? So that this kind of language methodology is in fact, is evolving very, very fast, and you have to adapt. And we have also to take advantage that now, even in REST, or even in Mare Nostrum, or even in CESBIMA, which is the computing center at UVM, so now it's more normal to buy GPUs instead of to buy CPUs. So my opinion is that CPUs is more now for post-processing or for processing the loops. No? But the core of the computation is made in GPUs. So we have to change our mentality to start learning about this kind of new steps, new just programming mentality. And we have seen also that in industry, they are lag behind. So in industry, the solver that I manage is still in industry. They are still in the previous steps. So they're still using CPUs and eventually maybe some in GPUs. No? This is at least my experience. So now somehow the universities and the research centers and REST try to push in the direction of the new language programming, the new standards.
One moment, Sergio wants to say something.
Thank you, Oriol. I try to get the mic. So, Eusebio, this introduced me one topic. So you changed the paradigm change on programming models, C, Fortran, now AI. But what about algorithm changes? So because you were introducing the point of petabyte of data. We are not ready for this. We've been able, the vendors, been able to change from CPU to GPU, so faster, more capacity, but we cannot handle 1 petabyte storage because it will take long to read and write. So you need to change how you are solving the problems anyhow. It's not a matter of applying the same methodology, not understanding what you said. Okay, you are applying now new methods, but for storage, volumes of data is critical. So how are you tackling this? Thank you.
It's a great question.
Yes.
Actually, we realize that, no? With all the message we get from support. And we are beginning to think a lot on online training. So generating the data and actually using the CPUs that we are not using because we calculate with GPUs, to use those CPUs that are not doing anything to begin to train. And then never store, you know? Just store things that we need for the checkpointing, but not really for the machine learning. This has some problems. It means that we need to know what we want to train exactly when we are running. But we believe will be, in the future, will be less expensive to rerun than to store. And this is a little bit where how we are changing things.
No, but I agree with you that we have to change the way of thinking. We have to change the algorithms. With the previous algorithms, it's not possible just to take advantage of all the different hardware.
And actually, Sergio, for sure, for this big channel, you have...
Yes, because I think that we have to change the paradigm. The point is that, for example, I had this discussion with some people from Italy that they are using one finite different code. With a finite different code, it's very simple to do the parallelization. For example, he has been able to move his code from CPU to GPU in a very easy way. So it's running now some simulations that are quite large. Okay? In my case, for example, I use something called pseudo-spectral methods. And for that, it's impossible. because I have to do a global all-to-all communication, and GPUs, until now, are not very good on that. So my code is now stop. I cannot continue. It's impossible. It's something stupid to put time there with, I know that it's not going to work. What is, for example, the future? Maybe your code, SOD to D. That's the let's say, the new architectures are used for your code.
Yeah.
Or for maybe find a difference, but my type of programming, or my method, pseudo-spectral methods, are dead after 50 years. Okay, and now they are going to extinction because we are not going to be able to use GPU with global all-to-all communications because of the bus. The bus size is not enough. Or at least this is what I understand right now, 2025 at this moment.
Yeah, and for the data is that we are thinking more on storing traditional data and on online training to do a reduced order model of the actual simulation that could be used for external users to have more advanced statistics. We will lose a little bit of accuracy, but they can download that, maybe gigabytes, they can download it and run it on their local systems and have actually something that is like our big simulation. This is what we would like to do on these big simulations. Let's see if we are able. No? Yeah.
In fact, this is one of the main problems now, but the data is huge.
Yeah.
Or we don't have data, or we have too much data. And when we don't have data, this is a problem because you don't have data, you don't know how to create the model. No? And in fluid mechanics, this is a problem, but not only in fluid mechanics. No?
No, in general.
In general. So this is the reason because now there is a lot of people just researching in how to create synthetic data, no? And how this synthetic data is related data or no. But then when you have a lot of data, no? The question is how to train your model with huge data. So sometimes we do, is just also in collaboration with Oriol and other people, is just to create, to reduce the data, using several algorithms. It is possible to reduce the data, no? Like autoencoders or singular decomposition, things like that. And then to train on the reduced space. And this is a problem because when you reduce the data, you are losing, obviously, some information. And you don't know if really your model will be accurate enough. But this is somehow, so the question is that for us, the more computational resources, the better. No? But sometimes, even with the complete computational resources in the world, we don't have enough. No? So this is the main problem that we are facing now. And it's funny what you mentioned, because I remember that at the beginning, when you started working with you, so everything was Alia with your solver. Yeah. And then suddenly, Alia disappears. No? And now it doesn't really disappear. No? But now it's up to D. And this is something that in my group, we are just discussing from time to time. No? We have our horses 3D with this high-order spectral method, and we say, OK, maybe this is all enough. No? And all enough means 3-4 years. No? We had to get rid of the solver to start from scratch, because this kind of new architectures is not possible to be implemented efficiently in the other solvers. So you need to go to new paradigms, to new reality from the beginning. No? I think this is the added value of 2D in this particular case. No?
Elena, yes.
There is also something I want to ask. As a user, I'm not a developer, we are expecting to see more general codes that are capable of solving different physics, because there is not only aerodynamics, there is thermal problems with radiation, and you want to, of course, your students want to use only one, because they want only to learn how to use one. And you have to improve the knowledge of all the codes you are using. So I'm expecting to see in a few years, like general code, we are very fond of OpenFOAM, that is CPU architecture based, to see that kind of codes developed for GPU, so we can integrate everything with the machine learning and the artificial intelligence. So I think TNEC is doing some fork with, that is called Spuma.
I believe there are several initiatives for OpenFOAM.
Yes, but still not a generalized software, open source, of course, that can be used for all the simulation in engineering. So I hope to see that also.
Okay. Oriol.
So You mentioned a couple of times that there is a need for new algorithms or that their current are not working properly. And I want to take the opportunity to do a small advertisement. So there was a program by EuroHPC to develop new algorithms. There have been 22 new from short URLs. So the thing is, if you were aware of that, or what would it be needed for you to incorporate these new algorithms that have been done, or what can you need for the future in case there is a new edition of these kind of programs?
Well, I was aware of that.
You are aware of that, I know.
I was reviewing.
You are the expert.
And it was very interesting, in my opinion. It was tough because it was kind of short, no? I was reviewing, so looking how the different projects they were advancing. But I believe it was impactful at the end. At least with the ones that I checked, they did new things that were interesting. And we need more like this, because at the EuroHPC level, usually there are very big projects, but small projects targeting a specific optimization with a collaboration of a couple of teams, that it's very much needed as well.
And you see that being implemented in the next couple of years in new applications?
Yeah, that could be possible. Yeah. Okay. I know that, for instance, some of those codes were as well on Center of Excellence, and they have benefit of that.
Okay.
So, yeah.
Good.
Okay. So we continue a little more questions? Yes.
Yeah, I have a question if there is. Hi, this is Gonzalo Merino from PIC, Barcelona. I have a question, maybe it's a bit related to something that you mentioned a while ago, but I'm curious about that. So, quick question. So you mentioned this paradigm happening in your field where you used to need hundreds of thousands of simulations with your classical algorithms, right? And now you find out that you run 10,000, you train a model, and then you can accelerate that. Could you comment on then how the trade-off in terms of resources ends up being? I mean, for for training that model on those 10,000 simulations, what's in the end the balance on the resources that you need? I mean, how many GPUs? I mean, what's the kind of, let's say, are these net savings in terms of overall resources, or what is the balance? How is the balance look like there?
Good question.
Okay, yeah. So what Eusebio is talking is more about research that we are doing with Airbus in particular. And the algorithms we are still developing, because the key is to understand the envelope of your optimization. And the main vision that we have is that we begin like with a traditional hypercube. We do a ROM of the initial simulations. And then we begin to see the uncertainties of this ROM. While we have more uncertainties, we begin to put new high-fidelity simulations, and we do the sleep until the ROM is able to be predictive on all the envelope, and then we stop. So this is very dependent on the target case that we have, right? Right now, we have been targeting flight conditions, and then as well, conditions that are more for the for high lift conditions, so when the aircraft is landing. That part is easy, but when we have flight conditions, you have chokes, and those chokes are very complex. So the trade-off is different, okay? Depending on which physical point you want to optimize. But you reduce a lot. And the other thing that we are trying as well is to do multi-fidelity, no? So maybe we are doing some simulation with GPUs, with our codes, but we do with the industrial code some simulation which runs that it's a steady state type of level of simulation. This is using CPUs. And then we mix this to do the ROM. And at the end, we can have big savings. I would say at least we use 30% of the resources that we were using initially, okay? But it's very early. We are experimenting a lot, and it's very dependent on what we want to optimize at the moment.
There is a typical example that is published in AWA, in which they explain how the design of the fighter is. No? So you have, in this particular case, that is already published a couple of years ago, in fact. No? So they mentioned that there were 19 design parameters. No? This can be geometrical, and this can be physical. No? Like Oriol mentioned, it can be the angle of attack, the Mach number, which is basically the velocity, Reynolds number, which is velocity and some geometrical parameters, and also a lot of just deflection angles, ailerons, or whatever. No? And you have also the range of these parameters. No? For a fighter, so the Mach number or the velocity goes to very small velocity, very low velocity, to very high velocity. No? For the Reynolds number, you have also a range, no? From 10,000 to 10 to the 5th or whatever. No? So that means you have to select, no? And you see, okay, if I want just to cover all my design parameters, I have 19 parameters. I have a range of different parameters, so that means that the number of simulation is 100,000. I want to cover more or less everything. 100,000 is unfeasible, or is feasible, but you need huge computational resources. And then you say, I will start with 1,000. So then you try to study your design of space. No? You have design of experiment. No? And then with some methodologies, with some algorithms, so you pick some of these parameters. No? You run the simulation and you create your model. No? And then you evaluate your model. You try to certify your model. No? In fact, you don't create your model with the 1,000 simulation. You create a model with only, for instance, 500 simulations. And then you validate your model with the remaining 500. Even to select these 500 between the 1,000 is a little bit tricky.
And we don't have a standard. We are actually learning how to do this at the moment.
Yeah. So this iteration, like Oriol was mentioning, and then you estimate the error and you say, okay, in this area I have a lot of error. No? Go back and to put more. And then again and again and again. No? Yeah. And everything is problem dependent. No? Everything is problem dependent. And we are still learning about that. Yeah. No? We are still learning how to just manage all this situation. In any case, it's important just to obtain an estimation of the error. No? So the simulation has an error, and the model has an error. No? So somehow the reference of the error is the reference of the simulation, or the wind tunnel in case that you have experimental results or whatever. No? You have to be able to estimate the error. This is not also sometimes possible or very easy. No? Okay.
Yes, we deal with the same problem. We do the same approach as you, as the use of the reduce order model, but the selection in the parameter space of what you have to feed that reduce order model is completely different. It's use case.
Yeah.
It's use case. And it has nothing to do, we don't see a pattern that we can reproduce. Sometimes we have surprises in for some models for the industry. We realize we have to do much more number of cases than we expected. So that's something that makes things very difficult. We cannot automate, or we can do an automatization of that, but the number of cases you will need to have relevant, control your errors relevantly is completely different. It's just case defined.
Okay. Any more questions? No? So the next question, that it has been as well a little bit tackled, but I believe it's interesting to talk about is, for you, what are the biggest challenges that we are facing for engineering and science if we want to really use machine learning as a standard part of our functions? No? And at the moment, for sure, we have problems like a skill gap, no? So we are not really trained on that. Actually, the algorithms are so fast appearing, no? You need to look at archives, no real journals, because it goes so fast. We need ways to integrate traditional CIA type of codes, could be fluid mechanics, finite elements for structure, etc., with machine learning. We don't have standards to do that. At this moment, in my group, we use a lot of smart Redis. That it's something that Bernat did, work a lot. And it's a library from Hewlett-Packard that allows us to have common memory buffers between the machine learning applications and the different traditional applications. But there is no real and standard way to do it. And each group is using its ways, etc. So this is, to me, a barrier, no? And of course, there is another barrier that is that we need a lot of computing time, storage, as we were talking. We need to understand as well how to select how to do the cases. No, I was on a project, a big European project, to do new turbulence modeling, and the biggest turbulence experts on models, were there, and they were proposing some cases. We ran the cases, did calculations, and then we realized that each of the cases was targeting more or less the same kind of turbulence problem. So the model was not really improving too much, So, but they were like very happy to use machine learning and not thinking about really the cases, So for your point of view, which are the biggest challenges that we should address? You want? Yeah.
I mean, I think first of all, there is the reproducibility kind of issue,
yeah,
right? So there's people publishing very fast, a lot of papers that we go through it, we see some results, and there's no like uncertainty quantification of the results. So when you train a machine learning model, it's a bit of a stochastic process. Maybe some trainings converge, some don't, and you have to do some kind of, to quantify this uncertainty. And a lot of papers, I don't think this is standardized, like to provide this uncertainty quantification. And I think this is very needed. Like, if you want your work to be reproducible and to be that someone else can benefit and use from it, this has to be established in the field. I also believe that something that needs to get established is like benchmarks. So there is a benchmark for automotive engineering, there's a benchmark for aircrafts, but there is not really benchmark for, in our field, for example, machine learning models for fluid mechanics in terms of inference, for example. You try to do a reduced order model, and in one, like an autoencoder, variational autoencoder, whatever you want. Can you first test that and compare the performance of that, what people have been doing in the past for that particular test case? How do you compare the works to each other? And I think that's very relevant. And one more thing, which I already mentioned before, is we need to learn from these models. We need to understand what they do to some extent. Because this is, I think, in my point of view, a very fair critic of machine learning is like, okay, it works, but why? And we need to, I think, spend more time thinking about this part, about why they work. I try to come up with post-processing tools for the machine learning model that we can get some understanding for, and link into the physics.
Sergio.
Yeah. Okay, I'm going to step out from fluid mechanics. Okay?
Yeah.
So I'm going to talk about, I'm an editor of one journal of engineering, results in engineering. We are in the top, I don't know, top 5, top 10 of engineering. And I'm in charge of the artificial intelligence part. And I'm receiving 80 papers every week, approximately, where I receive almost everything. In fact, I'm receiving a lot of papers about one kind of algorithm that follows the life or one kind of bird, ants, mammals, fish, spiders, and spiders from the other day I have one from the spiders from the north part of I don't know what country. So I think that we have a hype right now. Everybody's trying to move from typical science to AI science, and maybe 90% of this is absolutely useless. Because when you read the paper, before sending this paper to the reviewer, you say, but what's new here? It's only a new tool, but there's no new science. There's simply another way of doing something that we know perfectly how to do it, and there's probably classical algorithms that do this better. And this is a problem that we have right now, that everybody's trying to do this new science, but sometimes it's useless. We are just wasting time, paper, resources, and something like that. And as Eusebio said, one of the problems that we have also is the error.
Yeah.
Because the error is there. We know that when we are doing some model, we got an error. Is this error going down, going up? Can we check? Do we have a benchmark? No, we don't. And that's another problem that we are that we have right now. And we have to sort this out as soon as possible. But I think that the main problem right now is to try to use this tool wisely. We need to sort out this in 3-4 years, because if not, we are going to be buried in bad science.
Yeah, that's a great point. It's true that I was on one of this IA for Fluids conference, the first one, and my impression was, wow, all the PhDs that are here are just doing IA, okay? And they are doing particular things for a particular problem, right? But it was not generable. You could not use this on other type of problems. And this defeats a little bit the purpose of science, no? So usually you want to do a paper with something that others can implement, can use, no? And they will advance on that, and maybe if they will identify, this does not work, no? But this has been the way that our community has been growing. And right now, it's very hard to read a paper and reproduce that paper exactly on your particular framework, no? And that's a challenge. So now, yes, we can burn a lot of money, we can do a lot of papers and combine industry to begin to work with us, but after 3-4 years, they will realize, okay, this is not really advancing, and we could have like a reflecting effect, no? Then people will not be really open to continue working on machine learning and applying this to science. So that's a challenge for sure that we need to sort it out, no?
I would like also to add, apart from those already mentioned by all of you, and in fact has been also mentioned by Oriol, I think that another challenge is the quality of data. In fact, data itself.
Really, data.
Be able to generate data of high quality. Because we realize in different projects that there are not too much data. And generally, the data is also very expensive. No? In a complex configuration, keep in mind, for instance, that in a complex configuration, fluid mechanics, structural mechanics, acoustic, whatever. So each data could be around 100 million degrees of freedom. So each snap of your data, you have 100 million degrees of freedom, 100 million points there. It is only one data. No? Imagine you have to generate, I don't know, maybe 100,000 data, or 10,000, or even 1,000. No? So then to generate those data is a problem. And also, in engineering is a problem because the data should be physically relevant. No? It's not an image that you can create with some kind of diffusion algorithms or adversarial networks. No? So the data in fluid mechanics engineering, you have equations or you have physics. No? So those data should comply with some particular equations, physical equations. No? Okay, so this makes things a little bit, in fact, much more complex. No? And then when you have this data, and this is one of the problems, because this is the completely struggling. So who is running those data? Who is just computing this data? No, this is very, very expensive, no? Computing this data. Just before just creating the model. But obviously, good data means good models. Bad data means bad models. Okay? So it's a loop that are related to each other. No? So now we are working in how to generate synthetic data with physical background. No? It's important for physical problems, of course. And then we have this data. You have this data, so it's 1 million degrees of freedom each of the data. How do you train this huge data? No? How much computational resources, how much GPUs, how many GPUs you need to train this data? This is another problem, no? Another challenge. No? We are facing now in different problems, and we are facing now with industry. No? So it's a question of scale of the problem. Also, yeah?
Exactly, yeah.
About data, and I'm going to use that we are here at RES, because I have a problem with data. I generate a lot of data. My university told me that 1 month I was 10% of the data moving around in the network in my university. So the point is that when I'm sending data to some other universities, what we are doing now is to put that in one hard disk and move it by courier. I mean, it's impossible to do it in any other way. So I did this with some people in Australia, a lot of people in America. To open one server in my university is totally, absolutely, and completely forbidden, because I don't know how many rules I was going to break. If I open something to the internet, it's totally forbidden. So it is possible to create one repository in order that we can upload some data up there. And then make it sort of more or less easy to people that are working anywhere in the world to download this data. And I'm not talking about, of course, I'm not talking about a few gigas of data. I'm talking about 100 terabytes.
Yeah, petabytes. Go ahead.
Thank you.
Okay, well, I had a comment for the things that were saying before, then I pass the level to Sergi. The first thing is that in terms of reproducibility and data quality, and this is a problem everywhere in every single field of science, of research, and so whatsoever. And it's tackled from many people around. So I think that having also the fluid mechanics and the simulations community on board in this field is very, very important. And it's very, but there are already some solutions or some approaches out there that we can also share. On the other hand, we have in TRES, we have the data projects and the data calls, and they are just tackling the problem that you were telling, that people have sometimes a lot of data that are very costly to reproduce or to simulate, and you don't want to spend so much computing power, and it's much more convenient to store them somewhere near to the computing power, where you can just make other people profit and really extract information from there. So there are other communities that are doing it, and it will be very, very interesting to have also this use case there. So if you are, if you have a, Nadia Tonello, data manager. Sorry. So this is just a comment that I wanted to make. I'm sure Sergi has something more to say.
Thank you, Nadia. No, so this is exactly what we need, inputs from the community on what you need, but you are late, Sergio, on this one. So we opened data services since 4 years now, and those services are provided for excellent scientists that are coming with projects for storing and curating and providing data to the scientific community. So this is open call, 3-4 years time duration, but at the end, if you don't get an extension, if you are not keeping excellent and servicing data, we will remove the data, because the value of the data is, so the problem, data is easy to store, but it's difficult to create, it's difficult to load on the compute for using, and that was reason my former question, how to reduce the data, how to make sure that this data is capable. So now these days, maybe it's easier to get a new computation to get the data back again, but that's still expensive. So wind tunnel simulation, I understand, is very expensive, but all the others are coming expensive as well. So what's important is that you are building your business case, your scientific case properly, and your data management plan properly to make sure. But RES is available for you, for helping you on this, on petabytes of data for many different projects.
Good.
Yeah.
Yeah, in that sense, I think there's been a shift of culture a bit from the past. So in the past, when you were computing a temporal dynamic simulation, you wanted to take the average in time, you store every single snapshot. You keep all the data.
The old school guys, they were
you keep all the data, right?
Yeah.
And then you perform an operation, which is a temporal average, that you could have performed on the fly very easily. But you wanted to keep the data because data was expensive and was hard to get. Okay. We have been shifting to this kind of co-processing of data. When we run the simulation, we already think ahead of what we need to extract from the simulation, what statistics do we want. And then we compute them when we have them in memory loaded, because it's much cheaper and it's much faster. So now Oriol was mentioning something that's very important too, which is this kind of co-training strategy. When you have a machine learning model that needs to fit from data, I mean, you can use data that's being generated on the fly from a solver and use on other resources, maybe an idle CPU to train it.
Yeah.
And all this strategy of co-training, co-processing of the data, it's very important. So you have to think very carefully ahead of the simulation, how are you going to do that? And I think this is a culture shift that we've been experiencing, that it will become more and more important.
Yes, please.
Hi, I have a question regarding another approach about the ability of data. There has been different foundational models. For example, about time series, we have Chronos, we have Nixtla, and in the domain of DNA, we also have RNA-FM foundational models that have been trained with lots of information. And I was wondering if you are eager to, for example, fine-tune those kind of models. I don't know if in the domain of environmental situations, but what do you think about that, about reusing data that has been trained in different kind of applications of your interest?
Just to clarify, how does a foundational model, in your opinion, help to reduce the data part? Because I thought, in my opinion, it's more to generate the data. Like you can have a data-driven foundational model, like let's call it like a data-driven finite volume method that you can make simulations with. But in the end, you generate the data if you like. That's the point, no?
Yeah, I see it. For example, we're working with RNA. So you have this model that has been trained with, let's say, 30 million sequences. And we're trying to figure out the 2D structure of another sequence that hasn't been by the foundational model. And that would help us, that would guide us in that sense. So I was wondering if in that case, in your particular situations, would you reuse that kind of data as a foundational model? Or would you, as you said, would see some kind of drawbacks, or yeah, just to discuss it?
No, it's a great question that links with one of my questions that is the next one, is are we going to have foundational models for engineering? And we don't know, no? I give my particular view, and you guys, you can say, to have foundational models, we need a lot of data that is public, no? That everybody can interchange. In engineering, we have a huge problem, usually, that industry don't want to share data, okay? On research, yes, but then will be a foundational model of very simplified geometries and conditions, not the real ones that we need in order to have something that is kind of a Navier-Stokes really solver for any particular engineering thing. So we have, if I work with Iberdrola and I work with Ocean Winds, they will not share data about the wind farms. Never, ever. It's impossible. Actually, they will not share this wind farm data with people that is not part of their contract. Okay? Because it's very confidential for them. And Airbus, you can imagine the same with Boeing, Dassault, etc. No? So we have a challenge is, if we want to do foundational models, we need really community data, and I believe we are very far away of that on engineering, in my opinion. Okay? No. And then I don't know if technically it's possible. Maybe.
No, it's just the same. We had the same problem. We had a problem with the European Space Agency. So they, I mean, we could publish a paper, but the condition was that we have to remove all the numbers from the figures. So the figures are basically colors, okay? But you don't have any way of extracting the actual values from there. It was the only way. And also asking them, we were doing something about the plume, and we didn't have anything about the chemistry. We didn't tell us anything about the chemistry, nothing at all, because everything was forbidden to share. Yeah. So this is a problem. How we are going to do any foundational models about rockets if we don't know the chemistry? No?
Yeah, we don't have.
If we don't have any data, you cannot start from scratch.
Yeah.
And this is absolutely forbidden. And about fluid mechanics, the problem that with fluid mechanics is that we always focus in a very small part, in a very small details, in a very, let's say, detailed problem. So from that to move to something large that is good for everything, I think that is, at this point, it's impossible.
It's a dream, but
models are completely different. You have combustion problems and have nothing to do with wind flows we have in a city. So the diversity of the problems can be maybe too broad to make use of some specific problem, of the results of some specific problem. And I also dealt with the problems with the companies, so they don't want to share any data. So that's also a big question.
I don't know, Bernat, your opinion of foundational models?
Yeah, so there is, I think, for our field, or in engineering in general, a kind of not a clear definition of what a foundational model is. Okay, so maybe you can think of a foundational model as a finite volume method. That's a foundational model in the sense that you have a general toolbox that you give it some initial conditions, some boundary conditions, and some governing equations, and that gives you an answer. So that's very general, that's fundamental. But even in that case, sometimes finite volume doesn't, I mean, we need to tweak it a bit.
It's not general, no?
It's not general.
The solvers has his specific.
So you have to, you have discontinuities, you have to use limiters, you have many things, right? There's not really fundamental or fully general. So I believe that in our field, or in engineering in general, this goes kind of hand in hand of kind of a data-driven traditional methods that we've been using, like numerical schemes. Like you can have a data-driven finite element method or a data-driven finite volume that is specifically tuned to provide better answers for a specific problem. So you benefit from the fundamental nature of a numerical approximation of the governing equations, but you fine-tune that so that it gives you a better answer in the end that it would have given you like with traditional numerical schemes. And that is how I see a bit of, if you want to call that a foundational model, that is how I see it. I don't think we can call it like they do in natural language processing. Yeah. So yeah, large language models have been kind of tagged as foundational models because they have solved, I don't know, grammatical corrections, translations, I don't know. It's basically a text interpolator for anything, and that's very fundamental. I don't think we can have a tool like that based purely on data that can solve any flow problem or any physics problem. Like, I'm not super positive on that. Yeah.
Okay.
Yeah,
please.
Hello. One question to you, Oriol. Regarding the data, that we are worried about this because our research depends on data. You have said that you have contact with 2 companies and they will never share their data. My question is, have you ever asked to these companies why they don't want to share this data? And why, if you have done it, or perhaps you have planned to do it? And normally, as far as I know, companies want to share data if they take something that could benefit more than sharing this data and get, of course, LOPD, RGPDR, of course, it's a law and it's European. But if they have nothing that could make something wrong to their business, but the profit could be better. Because I have asked something to similar companies, but perhaps if I don't know the solution. It could be, okay, vectorized data or feathering learning. Or I don't know exactly. But have you think about this? Because
the problem is that the fluid mechanics data that in a wind farm, in particular, that we are talking, if you have that, you can calculate the power. And if the company is not saying for a particular day that this power is the correct one, they could have legal problems, you know? So they are worried that people try to, using this data, look if the power that they are saying that particular day they were selling from that wind farm was correct, okay? They could have problems as well for the computers, because the computers, they could understand the control, how they are controlling inside the wind farm, etc. Okay, so it's the main value of that company is to understand that wind and to have these histories to correct, no? That's a lot of money that they do. It's like the aeronautic industry as well, no? So all the design of an aircraft, for them, the real geometry is very confidential, and they don't want the computers understanding why they are putting those details, no? So that's the reason that with this data you can understand everything.
Yeah, but my question is, I don't have the answer, of course, but it's how we can do to use this data. I don't know, of course, but we are a lot of people here to think about how we can try to find a solution, or I don't know what, but to can use this data without a prejudice to the business. They cannot find out the thing that could be critical for the business. For me, it's what I am thinking about, because I think a lot of data, and not in the farm, but in other subjects, how we can get this data without prejudice this business. I think it's the key for, and it will increase exponentially the
To me, it's hard, If you talk with the traditional European industry, they never have shared everything between them.
Yeah.
Even sometimes, if they are on the same consortia, one of them leaves the consortia, and they want just to be alone with the rest of the universities on that particular consortia.
I'm just wondering, I want to share with you, because it's a thing that I think about that will, I think if we can try to solve this, the benefits will be very high. It's just an opinion, and want to share with you.
To me, it's a very tough problem, yes.
Thank you. So I wanted to comment that in Europe there is this activity that we have, that is Gaia X, is called, that is promoting the construction of data spaces. And it is mostly driven by industry that want to share data. Of course, in different fields like tourism or manufacturing or things like that. So I understand perfectly that in your case, it's so applied to a specific case of a specific company that want to solve, optimize a certain process. So it's really, really specific. But put it in a larger context, maybe there's something a little bit, I don't know, that can be really, really close to physics in this sense of fluidodynamics, that can be maybe shared between researchers. So
I don't know. You should really talk with those guys, because we are scientists. We share everything. Our codes are open. So it's not our problem.
Exactly.
You should talk with those guys and see. We have been working with them forever. And even in the same project, sometimes I have a data that the other partner does not have.
Yeah.
Okay? So, you should talk with them.
So, there are solutions or other communities that are trying to see if these bridges can be built somehow. Of course, everyone wants to keep their own secrets. It's theirs, but this can be also things that we can learn.
In fact, we can give you an example. We are now involved in a project with industry. They have developed their own model, but standard or previous model was typically polynomials, no? So, for instance, they want just to estimate the leaf, no? Has a function of different parameters. And they have a huge number of data. So they just tune the different parameters just to create this kind of polynomial interpolator, no? And then they realized that there is a new field with this machine learning, that the model could be more accurate with even less data, no? And they say, okay, why don't you start working into creating a model? And you say, perfect, give me the data. No. So they don't share the data. We have to create our own data and start working with our own data. They never share. But this is a question not for us.
Yeah.
This is a question for them.
Yeah.
For us, perfect. Like you mentioned, I publish everything. Everything is open. You can download it if you want it.
Okay, let's go to the next one. It's the last one. And it's more about the academic part, no? So you guys, you are all professor. Luckily, I'm not professor because I don't like to teach. Likely BSC exists, and until BSC is open, I will be there. But you need to educate new engineers and scientific researchers And you need to accommodate it as well on the program. So which are the challenges that you are facing? What are the things that you would like that is done, etc.? So maybe Elena first.
Okay,
yeah.
Thank you. Well, at present, we have all the people, the researchers that are doing our work in our group are all PhD students. They have to cover a lot of different subjects. They have to cover modeling, because in fluid mechanics you can have very different modeling depending on the problem. So that's a lot of knowledge you have to know which are the right equations and the more profitable ones, the more efficient, that you have to solve to have the dynamics of the fluid, or what is happening in that fluid. That is the first part, the modeling. You have to have also an expert in numerical simulation. So they have to know about, for example, in my field, finite volume methods, basically, and finite element methods also, and sometimes FSI coupling, so fluid structure coupling. So they have to know about that. And then they have to know also about running that in HPC environments, and also they have to know about reduced order modeling techniques, algebraic techniques, and also about artificial intelligence techniques. So it's very difficult to have that kind of profile, as you can imagine. And once you have that profile, you want to keep it forever. And usually they go. So it's really pretty tough. What I see now from my students is that there are some of them that they are more eager to work in artificial intelligence, and they forget about the physics of the problems, and they don't want to know about that. And I say, okay, physics come first, and then once you know the physics, then you can move to the numerical model, and when you convince me you know how to do it properly, then you can move to artificial intelligence. But I see that they are very eager to move to the artificial intelligence thing, because they know they are going to find works, very well-paid works, and a lot of experience that it's going to be very profitable for them in their careers. And I also see in workshops, you cannot go with a traditional engineering work. You have to add usually some artificial intelligence work, so the work you've done is more appreciated. So it's moving everything towards the artificial intelligence, and maybe the physics that is there, and we have to fulfill the physics first. It's something the students are not very eager to learn. So, and just finishing, there are few master studies that can cover all the specialities. There are some few examples in Spain, but there are very few, because our studies are very not flexible at all. So we cannot add some new subjects that are interesting for us and for our students, because we have to go through a lot of administrative stuff that takes 3 years to get the new program. So it's very difficult. There are few efforts in this sense. Few examples that work very well. Once in Galicia, for example, we have the Master of Mathematical Industry. It works quite well and covers most of these subjects, but there are a few examples in Spain.
Yes, okay.
Well, part of what you said about, in our case, I'm teaching in the Master of Aerospace Engineering, and this year we are adding one course about artificial intelligence. It's not part of the, let's say, a strong curricula, because it's impossible to change that without filling in 1,000 papers to ANECA. But we are giving this new course, and I'm going to teach that. And the point is that I still have to decide what to teach there. What is going to be useful for one engineer? All these things that we have been talking about, Sharp, Python, whatever, or about how to use one LLM wisely, how to create your own model, how to call one LLM using one API in order to get a lot of information, how to train your own LLM. maybe this is more useful to one engineer because only a 5% or maybe 10% of them will work with fluid mechanics. But all of them are going to work with LLMs because it's a new tool. It's like I'm not going to use calculators. I'm going to do multiplication by head. No, you are going to use your calculator. This is the same with LLMs. They are going to be forever. And we have to teach our students about how to use LLMs, about how to use all these tools. The point is that maybe we don't have to go to SHAP or to explainable artificial intelligence or something like that, and going more to go to a kind of artificial intelligence that can be useful for all of them. But we have to teach artificial intelligence because it's something that is going to be there forever. And hallucinations. Tell them about hallucinations when using LLMs. Because this is something that maybe they don't know, that at the end, the LLM is going to give you one answer. And it doesn't matter if the answer is right or wrong, and they can be very wrong. I remember asking for some references that was exactly what I was looking for. It was too good. And yes, the authors were for a Western from the 40s. So yes, I'm sorry, but at the end, I didn't use that reference.
Okay, we need to close, but just maybe, Eusebio, you can explain, because you are as well educating industry, no? Doing a special courses for industry.
I am somehow more or less in the same line of Sergio, no? That the program of aeronautics is not, it doesn't include machine learning so far. And in fact, if you want to change the program, you need 1,000 papers to the ANECA to change everything. So now, because this is a new field, and first you have to find researchers, professors, that they have experience in machine learning, no? At low level, of course. No? And then you offer, no, we are offering, we have the opportunity to offer machine learning courses in a new degree in applied mathematics at UPM, no? That started last year. No? And has been very well welcomed, no? This. And now we try to cover this gap in our school, just at the same, offer them master, no, for 1 year master, and we see that there are a lot of students interested. No? So normally we are in good position in our school, and also we try to take our experience with industry, no, to put this experience into the course. No? So we are a multidisciplinary team, we work in different fields, and somehow we experience in industry, but at the same time have experience in programming languages, in computing, and applied mathematics. So somehow we can merge everything. But still, we need more time just to put this on paper, just in the new program of, in this particular case, of aeronautics. No? So this is something apart from the aeronautic program. No? And then obviously, for our students, we have a lot of students just working in machine learning, and these are very good profiles. No? They are very good profiles, quite demanding profile, in fact. No?
Okay. Thank you, everybody. We need to close here. I hope it was interesting for you guys. And let's continue interacting these days. Thank you.
Thank you very much for your contributions. Thanks, Oriol.